All right, folks, this is the review for the forces points over points. I'll let you pause and read anything you need to. But question A says draw any remaining forces on the basketball and add positive and negative signs. Okay, so use your checklist. We must never forget this. Everything has a weight. So that's your weight vector, the earth pulling down on the basketball. There's no fan, so there's no mechanical. It's not touching a surface, so there's no normal. You need a normal force to have friction, because friction equals the fun formula. And there's no rope, so there's no tension, although you could say that this 16.3 newtons was caused, by the tension in the ropes of the net. But anyway, that's the upward force of the net. Okay, so was really just you got 3 points for knowing that there was weight and there were no other forces. Okay, then question B says, calculate the acceleration of the basketball while passing through the net. Now, remember, acceleration is the link between old school and new school. So that can come from, remember, there's 4 columns, or horizontal, which we don't have here because there's only vertical forces. So vertical forces, miscellaneous, which is friction and weight, and old school. And it wasn't obvious to me yet which column we were going to use, because acceleration could come from F equals ma, or it could come from old school. So let's go back and see what we know. We know the mass of the basketball, so let's use our miscellaneous column to calculate the weight. So 0.57 kilograms times 9.8 meters per second squared gives you 5.586 newtons of weight. Okay, so that's great. You're going to need that no matter what. So that's awesome. We have that. Now, we know now both forces. So that means the acceleration is going to come from the vertical column. But don't worry, you just set up all of your columns. You're going to use most of them. Again, we're not using the horizontal here because there's no horizontal forces. So vertically, you have to ask yourself, are the forces balanced or not? And those two forces are not the same. The upward force, you can see, is bigger than the downward force of the weight. So the forces aren't balanced. So instead of saying sum of the forces equals 0, we're saying sum of the forces equals ma. Oh, I forgot to put my plus and minus signs on my diagram. So the 16.3 newtons is positive. The earth is pulling down, so that's negative, equals m, which is 0.57 times a. And then that gives you 10.714 equals 0.57a. And then divide both sides by 0.57, and you get an acceleration of 18.8 meters per second squared. It's positive because the net is pushing up more than the weight is pulling down, which means that the basketball is slowing down as it descends. All right. Question C says find the speed, and that is definitely your old school column. Sorry, my tablet is not behaving for straight lines. Okay, so what do we know? We know V naught is negative 4.47. That's why I had you put the sorry, I'll start over. Okay, so filling out the physics Sudoku, You can see that we care about final speed. We know the time. So we're going to ignore the position function, and we're going to look at our velocity function. And we're looking for the final speed. The initial velocity, I should say, is negative 4.47 plus 18.8 times 0.094. Sorry about that. Didn't fit on the line. So V equals minus 2.70 meters per second. That makes sense that the basketball is still headed down, but with a slower speed because the net slowed it down. Okay, so again, moral of the story is use your checklist. We must never forget this. Set up your columns. It's not always clear which one you're going to use first, but if you get stuck on one, go to another one until you figure out what you need to know. Okay, number 2, Seth is jumping. And question A says, determine the acceleration required for him to go from rest to a certain speed in a time interval. So speed and time absolutely have to do with old school. So he is going from rest to a speed of 4.22, and we want to find A because that's the crossover variable, and we know the time is short. So again, we have an initial and a final speed, so we're going to use our velocity function. 4.22 equals 0 plus A times 0.096. That gives you an A of 43.96 meters per second squared. That should make sense because when you jump, right, you go from no speed to whatever your launch speed is in a pretty quick amount of time, right? That's why we kind of think it happens instantaneously, the time it takes you to kind of unbend your legs. So it makes sense that that's bigger than 9.8. Okay, draw a force diagram for Seth as he's propelling himself off the ground. So I chose to give this one to you as the practice because I think it can be kind of tricky. So again, let's use our checklist. We must never forget this. He absolutely has weight. Everything has weight. And ironically, that's sometimes the force that people forget about, especially in a problem like this where you, or like when somebody's landing in a net. And then you're focused on the force of the net, or like the basketball. So everything has weight. We don't care about weight if it's going left and right, but everything should have a weight vector. Okay, and then, so we did the weight. There's no mechanical forces. There's no fans. He is touching a surface, so there is a normal force as long as he's in contact with it, the jumping pad or whatever. So there would be no normal force on this diagram because he's in free fall, but there is a normal force here. There is no friction because he's not sliding across the surface, and there's no rope, so there's no tension. Okay, and now we want to determine the value of the normal force. That is a force, so we need to use the force column, which is the vertical. And he is absolutely not in equilibrium, or he would just be sitting there chilling and not accelerating upwards. So F equals ma. Did I say plus and minus? It's always a good thing to do. So we have the normal force, or, oops, I'm trying to get better by this, F sub normal minus F weight equals ma. We're looking for the normal. Let's go into the miscellaneous column to calculate his weight. So that's 65 kilograms times 9.8 meters per second squared turns into 637 newtons. Okay, so the earth is pulling him down, whether he wants it to or not, even though he's trying to jump up, with 637 newtons. And his got 65 kilograms of inertia that are resisting his change. So that's just mass, not weight. This is the pull from the Earth. This is how much he resists change, which is measured by his mass. Okay, so, oops, we know A. A is 0.096. That is positive because in order for him to accelerate upward, the net force has to be upward. Okay, so the force of the normal is, bring this over to the other side, 637 newtons plus 65 times, oops, that was the time. The acceleration was 43.96. Plus that, which is 2857.4 newtons. So the stress on this pressure pad is, this is what it would take if he were just at rest. There's a ton of force required to propel him upwards, which is, again, like if you think about somebody jumping off of a diving board, right, how much that diving board flexes to create that upward force. So if you add these two together, the total pressure at the surface is 3,494 newtons. It's not really pressure because pressure is newtons per square inch, but you know what I mean. Okay, so that is because it was a force, we're going to get it from the sum of the forces equals MA column. Okay, so this is very, very similar to what your points over points is going to look like. So hopefully this is helpful, and keep practicing.